This video is about the paper called Transferable Adversarial Training, a General Approach to Adapting Deep Classifiers. The paper starts by talking about domain adaptation, namely that domain adaptation is what enables knowledge transfer, which is the objective task, from a labeled source domain to an unlabeled target domain. This paper is mainly going to focus on adversarial feature adaptation, which is a mainstream approach for this domain. And this adversarial feature adaptation basically learns domain invariant representations. How does it learn it? It aligns the feature distribution or PDFs of the features of both domains. Now, in order to basically talk about the limitation of this traditional approach, which this work is specifically trying to target, they open up with the prerequisite of the domain adaptation, which is the adaptability. And how is adaptability measured? It is measured by the expected risk of an ideal joint hypothesis over the source and target domains. Now, to elaborate on this limitation and roughly speaking, what they say is that adversarial feature adaptation, which is the traditional approach, has the potential to deteriorate the adaptability. Why? Because it distorts the original feature distribution. Why does it do that? Because it tries to suppress the domain-specific variations. Now, this work's method is called Transferable Adversarial Training, or TAT, and this enables the adaptation of deep classifiers. The difference here is that this approach generates transferable examples to fill in the gap between the source and target domains. So it generates transferable examples. And the main contribution is brought in this part that says, they basically, so there is a theoretical learning bound, which is algorithmically guaranteed. So adaptability in this theoretical learning bound is algorithmically guaranteed, but without learning domain invariant representations, which was in the traditional approach, at the expense of distorting the feature distributions. So far we just read through the abstract, so let's go through the paper and see what exactly do they do. So the introduction starts with talking about transferring knowledge and its different motivations of such works. One thing that is important is here stating that deep neural networks are sensitive to cross-domain distributional shifts, which is kind of trivial. And then here is another important point. So this part is basically the history over the specific traditional approach that this work is trying to improve on. So let's read through it real quick. Domain adaptation aims at learning an accurate classifier for such a scenario. What is that scenario? Which is the scenario that models are trained on labeled synthetic data, which and they are being used on real-world data. As an example of a domain adaptation, which you have a labeled domain, a source domain, and then you have a target domain. And basically working with synthetic data is an example of that. So domain adaptation aims at learning an accurate classifier for such scenarios. Now, here, this part of the introduction goes through some of the references about how this was done before. A reasonable approach to domain adaptation is harnessing the power of deep neural networks to extract domain invariant feature representations. So how do we get these domain invariant feature representations? One possible way is that you choose a measure such as maximum mean discrepancy, and you try to minimize that measure, which measures the distance between source feature distribution and target feature distribution, and you basically minimize that, so you try to make your features that you are learning more domain invariant. Another example is basically adversarial domain adaptation incorporated into adversarial learning, such as two-player games, similar to generative adversarial networks. In this paradigm, you have a feature extractor and a classifier. Now, domain discriminator is going to be there to discriminate the source domain from the target domain, and then you use that to train the feature extractor in a way that it learns domain invariant representations. Why? Because the objective is to fool the domain discriminator. Now, here is where this work tries to shed light over the limitation of the previous approach. So what they are saying here is that based on the domain adaptation theory, this paper, an essential prerequisite for domain adaptation is adaptability. Now, here is the explanation of what they mean when they are speaking of the adaptability and this concept being linked to the potential limitation in the traditional approaches. What this says is that if you have the feature representations, adaptability can be explicitly quantified by the error of an ideal joint hypothesis on the source and target domains. Now, when the adaptability is poor, which means that the source and target domain are substantially different, we can never expect to learn a classifier with lower target error by minimizing the source error, because they are just different domains. Now, what they're talking about is that adversarial feature adaptation is risky when it comes to such situations. Why? Because the feature representations are going to be made domain invariant, and this might lead to distorting the original feature distributions, and therefore enlarging the error of the ideal joint hypotheses. Another disadvantage that I mentioned is basically the need of learning new feature representations in deep neural networks, and we know that there is no well-established deep architectures for learning many different tasks such as sentiment, polarity, classification dimension. And now these two main limitations are what they're trying to address in this paper. Now, what is the motivation? So recent advances in adversarial training has revealed that minimizing the error under adversarial perturbations within a small Wasserstein distance to the source domain can potentially bound the error on the target domain. And this also can help push decision boundaries away from the data points. Now, these are kind of like formulating the motivation for this work, which is essentially focused on generating new examples, kind of helping to make the decision boundaries more smooth and away from data points. Now let's go over the domain adaptation theorem. Let H be the hypothesis space, meaning that you can basically pick a classifier from it, such as classifier C that belongs to these family of hypotheses. And now if you want a generalization or test error of a classifier C on source domain, so let's say you have C and source domain, then this would be the generalization error of classifier C on source domain, and this would be the generalization error of classifier C on the target domain, which is XT. So let's go over this again. This is the classifier, this is the hypothesis space from which the classifier has been picked. This is the source domain, this is the target domain, and these two are going to denote the error or the generalization error of the classifier C or hypothesis C on source and target domains. Now, domain adaptation theorem states that for any classifier C, which belongs to this hypothesis space, you have this inequality holds. Now let's go through each one of these. So we mentioned that this is the generalization error of the hypothesis C, which could be any hypothesis from the family of hypotheses H. And this is the generalization error on the source domain. So this was on target domain, and this was on source domain. Now this distance here, which is measured for source and target domains, is basically defined like this. So for any two hypotheses in H, so you basically want to find the supremum of this set, this value, which is, let me first write it. Okay, sorry. So this is the value that we basically are trying to find the supremum for, which means that if you can pick any hypothesis, any pairs of hypotheses, any couple of hypotheses from H, and if on source domain they don't agree on basically the average of their disagreement is this, and then there's the average of disagreement on target domain is this, what is the maximum absolute distance or supremum of the absolute distance? Now, what is lambda here? Lambda is called, let's pay attention to the definition, error of an ideal joint hypothesis. So this time, let's say you have a H star, which could be anything. I'm sorry, it couldn't be anything, but let's say you basically want to find this. So you want to pick the hypotheses from the space that minimizes what? It minimizes the both of these at the same time, essentially. I'm sorry. So you want to pick the generalization error on the target and the generalization error on source. You want to pick the hypothesis that minimizes this, and this minimized value, which essentially is going to be the generalization error of this ideal hypothesis, which jointly is used for target and source domain. This thing is going to be the lambda, which is the error of an ideal joint hypothesis. So going back to this definition again, what this says is that the generalization error of classifier C on the target domain is less than or equal to the generalization error on source domain plus this distance-based measure and plus the error of the ideal joint hypothesis. Noting that this part is basically going to, so this part basically has to do with the feature distribution divergence between the source and target feature distributions. So this paper is primarily talking about the fact that, okay, when we use basically adversarial feature adaptation, we are focusing on this to minimize the divergence here, which was denoted here, but we overlook this part, and this work is basically going to focus on lambda. And the traditional approach basically focuses on the assumption that lambda remains small as they are minimizing this part. However, there is no guarantee for it. Now let's look at figure 2. So they bring an example of a case basically focused on such approaches. So on this part, you are seeing the VISDA 2017, which is a task of basically domain adaptation from synthetic images to real images. Now what they do is that first they want to kind of measure the adaptability. So in order to do that, what they do is that they have Resonant 50, they have domain adversarial neural network, and they have the maximum classifier discrepancy models. So it has 3 models. For example, Resonant 50 is pre-trained on ImageNet. So these are kind of like good models. And then by training them on both source domain and target domain, they can basically build a joint error. So here we can see that this is the source error. We can see the source error here is very small. And then there's a target error, which is larger. And then there's a joint error, which is larger than both of them. Here on the MCD, for example, we can see that the source error remains pretty small, but the target error is high. And when we look at these values, we can see that the joint errors are also high, indicating a smaller adaptability. They point out the fact that the MCD and DANN have basically are exhibiting a larger joint error, and compared to the non-adaptation approach, which is Resonant 50 pre-trained on ImageNet, is because these two adversarial based approaches are focusing on distorting the features, and they postulate or conjecture that this is actually the cause of this higher error. They also use basically the singular values of weight matrices between Resonant 50 and so the one that's pre-trained on ImageNet and domain adversarial neural networks, and basically they posit that given the distribution of singular values that are shown in this figure, in this one, so the fact that this is more heavy-tailed indicates that it is worse conditioned and more distorted in terms of the feature representations. To repeat the important parts of the work that we discussed, let's read through this part. So, motivation of this work. The above findings reveal that existing adversarial feature learning generally deteriorates the adaptability lambda and makes adaptation models vulnerable. Thus, we have to rethink the current paradigm and propose alternatives to the mainstream adversarial feature adaptation approaches. A natural solution is to fix the feature representations and instead adapt the deep classifiers, which apparently guarantees the adaptability lambda. This is possible by extending the adversarial training approaches to domain adaptation. Let's consider the problem of unsupervised domain adaptation. For that matter, you have NS IID observations from a source domain of distribution, namely, and you also have NT observations from the target domain of distribution. So note that the distribution for source is going to be P, and for target we're going to be Q. And we know that P is not going to always agree with Q. The goal is to adapt a deep category classifier, meaning that it can get deep features, and having F, we want to have basically a deep category classifier under the feature representation that we already have and we don't want to train, which guarantees lower generalization error on the target domain. To go a bit more into these notations, F being X being the entity observation, F is going to be the features, and this capital F is going to be the feature extractor. Then you also have domain discriminator. So this is the domain discriminator, which takes its features and gives us basically D. Now, in the context of adversarial training, D and F are going to form a pair, basically a two-player min-max game. D is going to be basically focused on distinguishing the source and target. F is going to be trained simultaneously to confuse D. This is the traditional approach. Now, what was the problem with this? The problem with this was that such procedure could affect the adaptability lambda, which could be potentially due to the fact that the original features are being deteriorated and distorted more severely. Now, in this work, a couple of things are important. One thing is that they propose to fix the feature representations. And in order to do this adaptability, instead, they do generate transferable examples and use these new examples to bridge the gap. Now, the losses that they consider are the following. They still have D, which was the domain discriminator, to basically distinguish between the source domain and the target domain. And for that, they use the following loss function. LD, the parameter of the discriminators, let me write it down first. So as you can see, in order to make this loss a small, D has to learn that whenever the features are coming from an example that belongs to the source domain, in order to keep this loss as small, D is going to have to say 1, and for the target, it has to say 0. Now, we also have the deep category classifier, which has this following loss. Again, we have NS source examples. For each of the examples, we have the cross entropy loss over the, so you take the features S, pass them to the classifier, and you also have the labels for the source domain. So the source was labeled in this context, and you also have this cross entropy loss. Before we proceed, also note that L2, this notation kind of indicates the L2 loss. One thing that is very critical and unique to this work is that F, which is the feature extractor, is not going to be updated using the gradients coming from basically working with these losses, and they propose to fix the features. Now let's talk about the most important part of this paper, which is basically generating these good examples. And what do we mean by good? The others by good mean that first, the features are good in basically confusing the discriminator, so that basically they help fill a gap between the source and target domain. And two, that they basically have to be able to deceive the category classifier such that they can push the decision boundary away from the data point. So the objective is to push or let's say help push the decision boundary away from data points. But this basically means that we're looking to generate new examples that makes basically both the discriminator and the classifier more uncertain, as well as they should not be too different from the original feature distributions. Now, how it is done is that first this is an iterative process to generate these new examples, and you need a sufficient number of iterations. They propose a k. So this is going to be the step index, and they say k, capital K, which is a number of iterations, could be something as well as 10. So what happens is that at a step k, for a specific entity you have, let's say, a target feature, source feature, and now you want to get from these to the next step of the iteration. So the way it happens is that, let's first go through the target. So looking at the discriminator, given these features, you have this gradient. Now you want to make this loss larger, so you want to propose a feature set that basically makes this loss larger and makes the discriminator more confused. So you're going to have to do gradient ascent on that. However, you want your features not to deviate so much from the original, so you also have to do gradient descent on the L2 loss between the features and the original. Now for the source, let me draw a line here to make it more clear. For the source, you have this. Now obviously you want to make the discriminator more uncertain, so you can look at LD. And you're going to have to do gradient ascent on this. You also want to confuse the classifier, so you also want to do gradient ascent on LC of FSK. However, you again have that L2 constraint, so using FSK of L2, FSK and FS0, you try to keep that one as well. And you do this iteration, so you basically do this for k in range k, and you obtain the final results that you're going to use. Now the next thing that we're going to have to basically discuss is that the category classifier C was intended to be robust to basically domain distribution shift. And they propose that in order to do this, when you have these transferable examples, they basically focus on the source domain, and they want to have accurate predictions for these transferable examples in the source domain. So they basically force this by adding a loss and kind of pushing the consistency between these and the original counterparts of these features. So for basically the loss function for the adversarial training of the category classifier, they propose is as follows. So you have the transferable examples. So for these number of source domains, you're going to have, for these number of source examples, you can have, or source originated examples, you can have this cross entropy term. And then for the target, since you don't want to use the labels, you have a consistency based measure, which indicates that if you feed these ft star of I, this is t, this is star of I, the results have to be basically consistent. And next, you also have to train the discriminator to also be better at distinguishing. So the LD is going to be defined as follows. Again, in the source domain you have and in the target domain you have this term. It's basically the same as before, it's just that you have f stars now. So they jointly minimize LD and LD adversarial. So they focus on joint minimization of these two. These are equations 4 and 9 in paper. And they basically use that to train D. And then there's 5 and 8 for C. And they basically have this overall optimization approach, which means that train the classifier and the discriminator such that this loss be minimized, which is LD and this is basically the final loss function. Here's basically the algorithm part of it laid out. Feel free to pause the video and take a read through these algorithm section. So let's go again back into the theory and see what this paper did. So this was based on the domain adaptation theory in theorem 1, and we had this inequality. Now this worked because they froze the features and they basically worked on that. They fixed the lambda and unlike the previous approaches that, based on this paper, allowed the adaptability lambda to potentially weaken, in this work it's going to be guaranteed to be fixed, so it's going to be a complementary improvement. And the other thing is that by training the category classifier on the source domain, TAT minimizes the error on the source domain. The other thing is to note that the examples that they built based on the descriptions that we presented earlier is going to be, pushing the decision boundaries away from the data points. Why? Because it's going to help confusing the discriminator. That is kind of like the incentive for pushing the decision boundaries away from the data points. It is worth noting that their codes are available at this link here. Now let's go over the experimental setup and their actual results and the tasks that they ran this framework on. So the first one is the Office 31 for visual domain adaptation, 4,652 images across 31 categories from Amazon, webcam, and DSLR. And they constructed 6 transfer tasks using these 3 classes, A to W, T to W, W to D, all the way to the end. They used the ImageClef DA, a dataset organized by selecting 12 common classes shared by 3 public datasets. Again, so they basically picked datasets like this. Feel free to read the paper for more details. We can see that the results on these 2 are actually pretty superior to the previous approaches. They worked on a couple of other datasets and domains as well. So for the multi-domain sentiment, this dataset was widely adopted as benchmark for domain adaptation dimension. And it comprises product reviews from Amazon.com in 4 product domains of books, electronics, kitchen appliance, and DVDs. They talk about the models they choose to work with here. For image datasets, they focused on Resonant 50, pre-trained on ImageNet to extract the original representations that they want to work with. For optimization, here they have some important information. They use Adam with initial learning rate of 1e minus 4. They have inverse decay strategy of the A and N. And they have this learning rate change. We can see that the results on other datasets are also pretty consistently good. Using scikit-learn and the Blue Moon examples, they basically ran a pretty nice and illuminating example here in figure 4. Here, basically the purple and red point and the yellow points are the source elements. The blue pluses are going to be the target elements, and then the dots are all the transferable examples. And you can see in this figure here how they basically help with pushing the decision boundaries away and how nice they look. And that basically concludes this video. Thank you so much.